All right, we're going to talk about random variables, particularly continuous random variables. All random variables, continuous or discrete, can be described either their PDF or their CDF. The PDF is the probability density function, probability of a particular outcome. Although for continuous random variable, then that particular outcome is infinitesimally small. The CDF is the cumulative distribution function, probability of an outcome that is at least as big as some particular value. With a PDF, we can calculate something like what is the probability that a random variable x will be between values a and b. Continuous case, we'd have to integrate, while in the discrete case, we'd just take the summation. You should remember this from calculus. Instead of a sigma to show the summation, we use that squiggly s thing, the integral sign. The CDF, the cumulative distribution function, provides a probability that some observation from x will be less than or equal to some value b, which is the integral up to b of that density function, the PDF. One of the most common continuous random variables is the normal distribution, which has that classic bell shape shown there. That's the PDF of the normal. The CDF for the normal is that one below, the kind of S-shaped function. The classic bell shape of the normal PDF is probably what you're most accustomed to seeing. The normal distribution is called normal because it's just that. It's common, ordinary. You see it all the time. It pops out in all sorts of different circumstances. Many statistics have a distribution that tends towards the normal distribution. We talked previously about the binomial distribution, which converges towards the normal. Lots of other distributions do the same. Also, the average of statistics such as the mean will often have a normal distribution too. We denote that as n mu sigma, where mu is the typical representation of the mean and sigma is the standard deviation. Now, a little flag on that notation. Sometimes people instead denote n with mu and sigma squared, the variance, instead of the standard deviation. Just be on the lookout. If someone writes n parentheses 0, 16, the second term could be standard deviation or it could be variance. Anyway, here's a nice example of PDFs from a paper by Jim Hansen on temperature anomalies, temperature anomalies in the northern hemisphere over land in different decades. It's a very nice illustration of how there's been a rightward shift of the whole distribution, and each one actually looks pretty normal. Relative to the earlier years, the 80s and then the 90s and the 2000s had sharp increases in the number of positive temperature abnormalities. Now, one of the things that makes the normal distribution actually kind of special, but because it's special, we see it more at the time, and then more common, i.e. normal. Anyway, a linear function of a normal variable will itself be normally distributed. If x is normally distributed, then y, defined as a plus bx, is going to be normal as well. Now, that's not universal for other distributions. It's just this class of Levy distributions of which the normal is one. Having linear functions of normal distributions being themselves normal is awfully convenient, and it's a big part of the reason why normals are so common. Linear functions don't break that normal distribution property. We often standardize normal variables to form other statistics. Now, despite the terminology, standardized does not quite have a standard meaning. Version 1 of standardize, which is more common in mathematical theory, is that to standardize, you subtract the mean and divide by the standard deviation to get something that's often called z, with z equal to x minus x bar divided by standard error. Z would then have a mean of 0 and a standard deviation of 1. But it could have large values, positive and negative. Another meaning of standardization, might call version 2, more common in machine learning algorithms. That version would scale everything to a unit interval, so all the observations are going to be squished between 0 and 1. That is again a linear transformation. Define w, take every value of x, subtract off the minimum, and divide that whole thing by the difference between the max and the min. Both z and w are going to have normal distribution, as long as the underlying x's have a normal distribution. Now, how normal is normal? Next, we'll talk about hypothesis testing. We'll pose the question, how big is big? Here we'll pose the question, how normal is normal? Yeah, we asked the big questions here in this class. Now, I've shown a simple experiment here using census data. There are in total nearly 200,000 people. Their average wage is about $38,000. But the standard deviation is huge because quite a lot of people reported zero wage. They're not working. They're old or they're in school or doing other things. They're not in the labor force. That histogram shows the distribution of wages. We can see far and away the modal outcome is a zero wage. And some people get a pretty large salary. So it seemed to be a tough test of the assertion that the mean has a normal distribution, even when the underlying data is quite non-normal. But it does. I formed little polls, sampling just 100 people out of that 200,000 group. I calculate the average within that little tiny poll of 100 people, and I plot that in the black bars there. You can see that actually, yes, somewhere a bit above 30,000 is actually a pretty common occurrence, even if I'm just polling 100 people. Out of those 100 people, typically 60-something will have zero values, so it's really just averaging a whole bunch of zeros with 40-something that are not zero. But if you look closely at the vertical axis there, I mean, there are some that are over 70,000. That's kind of a bad miss. But many others are genuinely pretty close, which is cool. On the left is a histogram of the average of those 100-person polls. The most common outcome is somewhere over 30,000, so pretty accurate. And there's some fraction of polls that give total wacko values, but overall they're good. Next step is ask, well, why to pick 100? What if I had a different number of observations in the poll? Okay, do it. Samples size 10, 50, 1,000, 10,000. That's shown in the picture on the right. On the horizontal axis, I have the base 10 log number of observations in the sample. So on the x-axis labeled 1, which in logs means 10 to the 1 power, that's 10 observations. 2 is 100 observations. 3 is 1,000 observations. 4 is 10,000 observations. You can sort of see the sprawl of different values in there. If I pick samples only 10 people, then outcomes between 0 and over 100,000. So 10 people is a pretty rough estimate. But you can still see there's a certain amount of bunching around the true mean, 30, 40,000. Then as we go to 50 or 75 observations in each poll, by the time we get to 100, I've really scrunched down the amount of variation there. It's even more squished down by the time we get to 1,000 in the sample, and much, much smaller with 10,000. It's squeezed tight. It looks kind of like a funnel of smaller and smaller range of outcomes as we use bigger sample sizes. We can see there's definitely an increase in accuracy as I increase the sample size. But with diminishing marginal returns. Going from 10 to 100 brings a huge increase in accuracy. Going from 100 to 1,000 brings a still noticeable, but much smaller increase in accuracy. Going from 1,000 to 10,000 is even smaller. For anybody who works in the polling business, that's one of the key insights. There are diminishing marginal returns as your poll sample size gets larger and larger. Later, we'll talk about some of the other implications from that. Now, in stats, we often want to calculate area under the normal distribution. It's a basic aptitude. I'll ask you on the exam. The standard normal, this is version 1 of standardized, has mean 0 and standard deviation 1. It's symmetric around 0. The total area under the curve, that bell shape, is 1. We often want to find areas of segments of that curve. The key part of the calculation is using the symmetry of that normal distribution. When you look up the value, commonly you get an answer to something like, what is the area to the left of -1? Or some other value. I've shown that there on the left graph. But what if you actually want to know the area in both tails farther from the mean than either -1 or +1? How do I calculate that? Well, I know the area to the left of -1, and then the fact that the normal distribution is symmetric means that the area is the same as the area to the right of +1. So the area in both tails is the sum of those areas. And the area in the middle is 1 minus the sum of those areas. So as long as I know the area of that piece on the left-hand side, I can figure out the other pieces with just a bit of arithmetic. Doing those calculations in R is use either p-norm or q-norm. Look at the help function. For that, it's pretty straightforward. If you need to find areas under the normal, you can Google, you can ask Siri or Alexa or whatever your favorite sage. You can even do it in Excel. I'm not going to get into details for now, but the lecture notes have some good instructions on that. The normal distribution is really surprisingly common. That's why it's called normal, even though there are aspects to it that are genuinely kind of weird.